We are now going to start looking at some of the specific reactions of alkenes by these addition type mechanisms. The first one we're going to look at is called hydrogen halide addition. If we look at our observed reaction, we can see that we start with an alkene reactant and that our reagent is hydrogen attached to X, where X is a halogen, chlorine, bromine, or iodine. So for example, HCl, HBr, HI. This is actually usually done with gaseous hydrogen chloride, or at least non-aqueous, where we would run it in a solvent other than water. In this reaction, we would see that the hydrogen would act like an electrophile because it's an acidic hydrogen, so it should have a partial positive charge and be attracted to bases, and then the halide would attack like a nucleophile. The overall structural change would look like this. The double bond would be converted to a single bond. We would then make a bond to hydrogen on one of the carbons of the double bond and to halogen on the other side. So that what we've done is we have essentially added a hydrogen and a halide, hence the name hydrogen halide addition. In most cases, this reaction follows perfectly the mechanism, the general mechanism that was presented earlier. We start with our alkene reactant and the hydrogen halide. The hydrogen would have a fairly large partial positive charge because the halogen is very electronegative. So the alkene pi electrons would be attracted to the hydrogen and make a bond. Since hydrogen in most cases can only have one bond attached to it, it would let go of a bond on the other side, which would go onto the halogen as a pair of electrons and convert it to a halide ion. This would create an intermediate that looks like this, where the double bond is now a single bond. The pair of electrons that was in the double bond is now attached to the hydrogen, attached to one carbon, and the other carbon lacks a pair of electrons, so therefore it would be a carbocation. If the carbocation can rearrange to become more stable, it will. Once it's done rearranging, a nucleophile can then react with the carbocation carbon using a pair of electrons to make a bond to that carbon and produce the product. This reaction is not stereoselective. We form both syn and anti-stereoisomers. This can become very complicated, and so care must be taken to really analyze each of the stereochemical outcomes. It's possible to have up to 4 different stereoisomers for the products. When unsymmetric reagents, in other words, reagents where the electrophile and the nucleophile are not the same, react to an alkene that is also not symmetric, in other words, where there are different substituents on the 2 carbons of the alkene, then we can produce constitutional isomers. Here's an example. Imagine that we used this alkene as the reactant. The 2 carbons of the alkene are not equivalent. The left one has a methyl and a hydrogen, whereas the right one has 2 hydrogens attached. We're going to label these 2 carbons as A and B. So now imagine what would happen if we reacted that with hydrogen halide. If we reacted with hydrogen halide and carbon A made a bond to the hydrogen, then we would get this intermediate, which I have labeled A. The carbocation would be on carbon B. If then the nucleophile reactant made a bond to carbon B, that would give us this product, which we call product A. In contrast, we could also react and carbon B could be the carbon that makes a bond to the hydrogen, in which case we would get this intermediate where the carbocation is on the middle carbon, or essentially on carbon A. The nucleophile would attach to that, and we would get this product. If we carefully examine these two products, you can see that these would be constitutional isomers of each other. We have these 3 carbon chains with a halogen substituent either on an end carbon or on the middle carbon. We are going to call these possible products. When there are possible products that are constitutional isomers, we say that we have Regio Isomers. When we have Regio Isomers produced, one of our first concerns will be to see if there is a preference. So we have multiple possible products, but will any of these be preferred, produced in higher proportions? In the hydrogen halide addition, we see regioselectivity. Of the possible regioisomeric possible products, one is preferred. The scientist who first studied this was a Russian scientist named Markovnikov. And the regioselectivity preference has been given his name. It's called Markovnikov's rule. Markovnikov's rule can basically be summarized such. If we add a hydrogen and a nucleophile to an alkene, the hydrogen will prefer to attach to the carbon of the alkene that already has the most hydrogens attached. Or we could say hydrogen prefers to attach to the less substituted carbon, has more hydrogens, fewer carbon groups. This rule was initially determined experimentally. It was an empirical rule. However, now that we understand reaction mechanisms, we can explain it by looking at the possible ways that the mechanism can occur. What we're going to do is define a new step called the product determining step. When we have regiochemistry, what we will see is that the mechanism splits into 2 parallel pathways. The step in which it splits is called the product determining step. Essentially, once a given molecule has reacted either in one direction or the other, then it will continue to give a specific product. So the direction that it chooses to go in this split will be the direction that determines the final product. So a product determining step is an elementary reaction or a mechanistic step where the reaction splits into 2 different pathways that ultimately lead to different regioisomers, different constitutional isomers. Whenever we want to explain regioselectivity, we must identify the product determining step. It'll be recognized because that's where the mechanism branches. In our particular example, if we look, step 1 should be the product determining step. When we did our example, we said that in the first step, the hydrogen could either attach to one carbon or to the other carbon. These would produce constitutional isomers of the intermediate, which would then produce constitutional isomers of the product. once those two paths split, what we find is that the fastest path will produce the largest amount of product. Therefore, what we want to do is look at the two paths and determine which path would be faster. Well, when we talk about the speed of a reaction, we're talking about kinetics. And in kinetics, what we saw is the lower the energy of the transition state, the lower the activation energy. When a reaction has a lower activation energy, it will go faster. So what we need to do is we need to get information about the relative stabilities of the transition states for the two paths. Unfortunately, this can be very hard to do because it's almost impossible to directly observe transition states because, by definition, a transition state is the least stable structure in all of the molecules in the pathway, and therefore it will have the shortest lifetime, and it will be impossible to isolate because it will really desire to lower its potential energy and change into a different structure. We can, however, make a guess about the properties and energy of the transition state by looking at the structures of the reactants and products and the way that the energy changes as they move from one to the other. This was first proposed by a scientist from Caltech named George Hammond, and it has become known as the Hammond Postulate. The Hammond Postulate isn't perfect, but it relies on some pretty simple assumptions that are fairly reasonable in many cases. What Hammond did was he looked at the shapes of the different reaction energy profiles for a single elementary reaction step. What he decided was that there were basically three different possibilities for these energy profiles. A reaction could be endothermic, where the products have a higher potential energy than the reactants. A reaction could be exothermic, where the reactants have a higher potential energy than the products. And then there's a third type called isothermic, where the reactants and the products have the same energy. And we're not going to discuss that because isothermic reactions should have no preferences. He then looked at what these graphs of these two different possible energy outcomes tell us. To understand what he learned from this, we have to once again review these graphs a little bit. The important thing is to understand what this axis really means. This is the reaction coordinate. It was recognized by that time that what the reaction coordinate really represented was a series of infinitesimally different structures that are gradually changing, starting from the reactant structure all the way to the product structure. So these represent structures. It was also recognized that as you move farther along this axis, the amount of changes increases, and so therefore, when you look at structures from 2 points that are close to each other along the reaction coordinate, structure here, structure there should be very similar, whereas a structure that's far away, a structure here, a structure over there, should be very different. So the closer the points are on the coordinate, the more similar the structures. The farther away, the more different they are. He also made an assumption about the way that the energy changes. If we look at the shape of this curve, he assumed that it would essentially be sort of a parabolic shape, and that the two arms of the curve, the two sides of the curve, would be symmetric. They would go up and they would go down at the same rate. Because of that, he was able to determine that the center of this parabola should be farther away from whichever species, either the reactant and product or product, that was farther away in energy. For example, in an endothermic reaction, we start way down here in energy. As we go up in energy, we have to change the structure more and more and more and more. Because this energy change is so big, the structure will change by a lot. Whereas if we look on the other side at the product, because we go down, our energy change is so much smaller, we move along the reaction coordinate far less. So in an endothermic reaction, the transition state should be more similar in structure to the product, and it should be not similar at all to the reactant. The opposite would be true in an exothermic reaction. The reactant would start at a very high energy. We would not have to move very much to get to the transition state. So the transition state would look like the reactant, and then it would change a lot as we go down to the product. So the transition state would look very different from the product. This is summarized here. In an endothermic reaction, the transition state is similar to the products. In an exothermic reaction, the transition state is similar to the reactants. The significance then would be that if we change the structure of the product in an endothermic reaction and the energy of that product changed, the transition state energy should change in a similar way. Whereas in an exothermic reaction, changing the structure of the product should have very little effect on the structure of the transition state. If we go back to our particular reaction, our particular mechanism that we were examining, we would suspect that the first step should be endothermic, because we start with reasonably stable reactants and we change into a carbocation, which has a much higher potential energy, and even a halide ion. Ions should have a higher potential energy than neutral molecules. So we would expect that we go up in potential energy, starting from reactant of the first step to the product, making the first step endothermic. In that case, then, what we would want to know is, how does the stability of intermediate A compare to the stability of intermediate B? We would see that intermediate A is a primary carbocation, which has a much higher potential energy than intermediate B. So therefore, intermediate A would have a higher potential energy, intermediate B would have a lower potential energy. So, pathway A produces a primary carbocation, pathway B produces a secondary carbocation in its first step. The secondary carbocation is more stable, so therefore pathway B should be faster, because more stable intermediate would also mean more stable transition state, because the transition state looks like the intermediate. Therefore, we expect pathway B to be faster and product B should be preferred. This would explain Markovnikov's rule. If we go back and look, the preferred pathway is the pathway where the hydrogen attached to the less substituted carbon. This would produce a more stable carbocation and make that pathway faster. Markovnikov's rule said, in general, what we see is that hydrogens prefer to attach to the carbon that has the fewest substituents, is less substituted. So this explains Markovnikov's rule. In general, then, we would really expect this to apply to all different types of electrophiles, even when they're not hydrogens. And in fact, we observe this. But Markovnikov's rule itself really spoke specifically about reactions that add hydrogens. Now, there's one problem with Markovnikov's rule. When Markovnikov published his research results, there were scientists around the world that immediately tried to replicate those results. And in general, they saw the same results as Markovnikov for hydrogen chloride and hydrogen iodide. However, with hydrogen bromide, some labs reported the exact opposite result. They reported that with hydrogen bromide, they were seeing the hydrogen preferring to attach to the more substituted carbon. This regiochemistry was called anti-Markovnikov because it was the direct opposite of what you would expect with Markovnikov's rule. Unfortunately, this created a large amount of scientific controversy at the time. And the reason wasn't really resolved until long after Markovnikov passed away. It turned out that the problem was, if the research labs that were trying to replicate Markovnikov's work were not very careful, if they didn't purify their reagents and take care to exclude oxygen, then a small amount of a substance known as a peroxide would be present in the reaction mixture. Peroxides are spontaneously formed by organic molecules that are left in contact with oxygen for a long period of time. In careful experimental work, we would purify the reagents and there would be no peroxides. But if we weren't careful, there certainly could be peroxides. Peroxides cause this reaction to go by a different mechanism which doesn't use carbocations. It uses what are called free radicals. We're going to discuss free radicals in a later chapter. At that time, we will explain how this results in an anti-Markovnikov thing. For right now, what you need to know is that for hydrogen bromide only, we need to be concerned about whether there are peroxides or not. If peroxides are carefully excluded from the reaction, it will proceed in the normal fashion with Markovnikov regioselectivity. However, if we are sloppy and peroxides manage to make it into the reaction mixture, then it will produce the opposite regiochemistry. Sometimes we take advantage of this because there are times when maybe we want that Regio isomer, in which case we would then intentionally put peroxides into the mixture.